Learning target 6 is directly related to what we did yesterday, or I guess 2 days ago, learning target 5, all right? We're still talking about applications of exponential functions. In this case, we're doing them all with the number e. So when you see an e in an equation anytime, that's just like pi. It represents a number. It's not an actual variable, all right? So e is equal to 2.718-ish. It's irrational like pi. It keeps going on forever and ever and ever, but it's a number, so keep that in mind. Do not think it's a variable you're trying to solve for. In your calculator, there are 2 places you can find e. You have e to the x above the ln button, natural log button, below the log button. That's if you want to raise it to some power. Or you just have e above the division symbol. So if you're not trying to raise it to a power, you just need to use e. There it is. Okay, so both places. So we'll be using those today. Again, e to the x is just an exponential function. It's got a variable in the exponent, so it's still exponential. It still follows all the same properties. So it's still going to have an asymptote somewhere where it hugs some sort of horizontal equation, all right? And then it's going to increase, or it's going to decrease and hug somewhere, all right? So you have the same situation. So if you type all these in, e to the negative second is still 1 over something, so you still have a fractional value. E to the negative first, again, is still a fractional value. E to the 0 is just a number to the 0 power, and any number to the 0 power is still 1. So I can figure out what all of those are. We've got approximately 0.135, 0.368, 2.718, and 7.389. If you graph this, again, you get the same idea that we had in learning target 4. We're going to use e and e to the x a lot in the second half of this unit, because they directly relate to when we start doing natural logs and logarithms. Questions so far? So then, just like in learning target 5, we have growth and decay and interest equations that use e specifically. All right. The first one I want you to know, but a lot of the time we're not going to have to actually fill this one in. They're going to give you some equation for exponential growth and decay in terms of e. And then the compound interest equation is a little bit different from the one before, and it has a specific use. So we'll talk about both of those. So in the growth and decay equation, you have n, where that's still the final amount, and n sub 0 is still the initial amount. But then you have e to the k times t power. Well, k has to be some constant. Generally, we don't know that constant, and they're going to give it to us, or they're just going to give us the equation. And t is still time in whatever units it decides it's going to be in. So generally, you're going to be given an equation for this part, and you just have to use the equation to answer questions. I told you I'm giving you all of the equations on the quiz that you need. I didn't even put this one on the quiz because you won't actually need this equation to fill in. You just need to be familiar with it so that when they give you an equation, you know how to use it. Okay? The second equation we're going to use a lot more often, and it's for compounded interest. So we have a compound interest equation from Learning Target 5, right? Again, compound interest specifically relates to money. You have some sort of account, and you have your interest being gained on that account. So it has to say that the phrase compounded somewhere in it for you to use that equation. Here, specifically, you have to have continuously compounded interest. If it says compounded quarterly, you still have to use the equation from Learning Target 5. If it says compounded continuously, you have to use this equation. All right? So again, same values as before. A is the final amount, P is the initial amount. You have e to the RT, so R is still your interest rate, and then T again has to be time in years. But again, this only works for interest that's compounded continuously. It has to say that exact phrase in the question in order for you to use it. Everyone okay with that? So I've got two examples. One for each equation. Bakersfield, California was founded in 1859 when Colonel Thomas Baker planted 10 acres of alfalfa for travelers going from Visalia to Los Angeles to feed their animals. The city's population can be modeled by the equation, and it gives you a nice exponential equation, where T is the number of years since 1950. So that's going to be important later. Now this model is just like what we just saw in the equations. You have n equals n sub 0 e to the kt. That is the exact same format. Okay? So part A says, has Bakersfield experienced growth or decline in population? We don't necessarily have a rate here. We have k that's some constant, but the same thing applies from Learning Target 5. If your constant is positive, you're looking at growth. If your constant is negative, you're looking at decline. So are we looking at growth or decline? Growth, because our constant is positive. Questions about that? B, what was Bakersfield's population in 1950? Well, again, T is the number of years since 1950. So if it is 1950, that's your starting point. So what number represents your starting point? N sub 0, which is 33,430. If you weren't sure, if T is years since 1950, and you're trying to figure out T for 1950, and how many years has it been since 1950? 0. So you just put 0 in for the exponent, you get the same answer. That's e to the 0 power would be 1, and 1 times 33,430 is 33,430. And then C says find the projected population of Bakersfield in 2010. So we're actually going to use this equation. Again, T is years since 1950. So how many years is 2010 since 1950? 60. So e to 2.382 power times 33,430. Complete approximately 361,932 people. If you don't talk about population, you can't have 0.04 of a person. If you round it down, that's acceptable too. Question. On the second example, we're talking about compound interest. It says the Kwans are saving for their daughter's college education. They deposit $12,000 in an account bearing 6.4% interest compounded continuously. How much will be in the account when Ann goes to college in 12 years? So again, it says compounded continuously. That's the only reason I know I need to use this specific equation. If it had said compounded quarterly, you have to use the one from Learning Target 5. So we have A equals P times e to the RT power. So what's your initial amount invested? And what is your interest rate? And how many years? So the account would yield approximately $25,865.41. Questions about where that came from? That's it. Learning target 6. Any questions about learning target 6?